Hello. I would like to begin talking to you about sectoral structures theory. This is a theory I've worked on for the past few years. It's a mathematical framework that is built on the study of combining circular sectors with a lot of applications to geometric combinatorics, various types of algebras, even some number theory. We will begin with basics, and as we go on, we will see some very fascinating emergent properties from studying these sectors. Let's begin with the very basics of what is a circular sector. Basically, if we have a circle and we have an angle theta within that circle, we will refer to this as the central angle if it's right from the center of the circle. We will be using radians throughout this study to make things easier. So the length of this arc, as we know, the length of the arc formed by the angle theta will be simply r times theta, where r is the radius. Now, throughout this theory, we will assume the radius to be 1, because we're really not so much focused on the geometry as much as on the combinatoric aspect. So when the radius is 1, it will simply mean that the length of the arc is equal to theta. Similarly, the area of the arc will be given by theta r squared over 2. If r is 1, then the area will simply be theta over 2. Now, as we study the circular sectors, we will assume that we have a circle divided into congruent circular sectors. And this will probably give you a hint of why we're going to see a lot of applications to number theory as well, because we're really defining how we're going to divide these arcs. So we have a circle, we're going to divide it into n congruent sectors, and as such we will say that the length of each arc, or in other words, the measure of the angle in radians, will be 2 pi over n. That's very basic. Now we will refer to functions that use n, which is the number of sectors, the number of congruent sectors. We will refer to those as central angle functions. So we will say, for example, theta of n here is simply going to be 2 pi over n, which is a simple reciprocal function. And as such, as n goes to infinity, theta of n is going to go to 0. Now we're going to look at more complicated or more complex forms of this as we go on. Let's begin with an example. So we have the circular sector here that has an angle of theta, and we're going to assume a radius of 1 going forward. We have a chord between x and y. We're going to say the length of this chord is equal to a. So what is the length? How do we measure the length? We can simply draw this right triangle here, and we do a little bit of trigonometry to find that half of a is equal to sine of theta over 2. Just to pause quickly, we're looking at half of the angle here, that's why it's theta over 2. And since this only gives us half of A, then A is going to be equal to 2 sine theta over 2. Now we're going to convert it to this form using n, and we're going to say A is equal to 2 sine pi over n. And we're going to see that this makes it easier when we're studying certain limits, as we can take, as n approaches infinity, it can be reduced. So A is going to be equal to 2 sine pi over n. Similarly, if we're interested in h, which is this length here, we're going to find that h is equal to cosine of theta over 2, which is equal to cosine of pi over n. Now we're still here within the geometry. This won't last long. We're soon gonna stop talking about geometry and focus on combinatorics. But this is good for the introduction. Now, we're gonna also talk about the focus of the sector. So if we have a circular sector, we're gonna inscribe a circle within this sector, and we can see that the the radius of the circle will depend on theta, because we're assuming the radius of the sector to always be 1. We're going to call this small radius as a capital R, and we'll see that we're going to find many interesting relationships here. So for example, if we look at R, which is the distance here or the radius of the smaller circle, it's going to be perpendicular to this side here, which goes from this vertex of the sector all the way to the point of tangency between, or one of the points of tangency with between the edge and the inner inscribed circle. And we also have, to complete this right triangle, we can look at the distance between the focus, F, and the vertex. And this gives us a right triangle here. And we see that we're going to call this FL, focal line, which is the line between the vertex and the focus. FL is going to be equal to 1 minus R. So we know that the length, the total length here from the vertex to this point of tangency is equal to 1, because it's a radius of the sector. We remove R from it, and we are left with this focal line. So FL is the big radius minus the small radius. We assume the big radius to be 1, and that's why we say FL equals to 1 minus the small radius. So that's the first geometric relation to keep in mind. Similarly, we said we have a right triangle here. We're gonna call, again, we said this is FL. We're gonna call this side as TL, or tangent line. And we will say that FL squared is equal to TL squared, this is TL, TL squared plus the small radius squared. I hope this is clear. We have it here in an isolated form. So we have TL, FL, and R, where FL is the hypotenuse. Also keep in mind that this angle is going to be half of theta. So again, we're going to see the theta over 2 is very helpful. Now going back with simple algebra, TL is going to be equal to the square root of 1 minus 2r. And additionally, if we want to get the, if we want to look at this angle, which is theta over 2, we're going to say that sine of theta over 2 is equal to r divided by 1 minus r. So let's look at this again. This is theta over 2. This is r. And the hypotenuse is going to be 1 minus r. Again, if we look at, if we rearrange this, or if we solve it algebraically, we're going to get r, which is the small radius of the inscribed circle, is simply going to be sine of theta over 2 divided by 1 plus sine of theta over 2. And this will give us probably the simplest way to express r in a single variable using theta. So I'll write it here again. R equals sine of theta over 2 divided by 1 plus sine of theta over 2. Thank you.